You ever like look in a mirror and just think about how weird it is? Like it's just this piece of glass, but it shows you like a perfect copy of yourself.
Yeah, it's almost like magic, right?
It is like magic, but it's physics, you know? So today we're gonna deep dive into the physics behind mirrors.
That's right. We'll be looking at a really cool open source physics simulation called Simple Ray Diagram for Mirrors.
Okay, I'm intrigued already. The name sounds pretty straightforward.
Yeah, it is.
Yeah.
And it comes from, let me see, Open Educational Resources / Open Source Physics at Singapore.
Oh wow, so Singapore,
Yeah,
nice.
it's a great resource for anyone who wants to learn more about physics.
So the simulation's gonna like show us how mirrors work, like on a deeper level.
Exactly. It uses something called ray diagrams to help us visualize how light reflects off of mirrors.
Okay, so ray diagrams, what are those?
So basically, imagine you have like a candle in front of a mirror.
Okay.
The flame of the candle, we'll say that's a height 8 above the mirror.
Okay, so H. Got it.
Now, light is shooting off of that flame in like all directions, right?
Right, all over the place.
And some of that light hits the mirror.
Okay, so far so good.
A ray diagram just like traces the path of those light rays to see how they bounce off the mirror and where they end up.
Hmm. Okay, I think I'm starting to get it.
And the cool thing is, this simulation lets us do that interactively.
So we can like see how the light rays change as we move things around.
Exactly. And that's how we can see why we see a virtual image in the mirror, like a ghost of the candle behind the mirror.
Oh, okay, so that's what a virtual image is. It's like a reflection, but not really.
Yeah, it's not a real image that you can like project onto a screen or anything. It's an image that our brains create based on how the light rays hit our eyes after bouncing off the mirror.
So it's like a trick of the light.
Kinda.
Yeah.
It's more like our brains are interpreting the light in a certain way.
Our brains are doing all the work.
And the simulation actually shows us that this virtual image always appears the same distance behind the mirror
Behind the mirror.
Yeah.
Okay.
as the real candle is in front of it. So like if the candle is h distance from the mirror, the image will also appear h distance behind the mirror.
Oh, wow. So there's like a symmetry to it.
Exactly. And that's all thanks to the way light reflects.
Hmm.
You see, there's this fundamental law in physics that says the angle at which a light ray hits a mirror is always equal to the angle at which it bounces off.
Oh, so there's like a rule to it. It's not just bouncing around randomly.
Nope. There's a pattern, and it's a really important one.
That's pretty cool. So how does the simulation show this? Like how does it help us see this law in action?
Well, it uses something called principal rays.
Principal rays. Okay, more new terms.
These are specific light rays that help us understand how an image is formed. For example, think about the ray that leaves the top of the candle flame and hits the mirror at a distance h below the flame.
Okay, I'm picturing it.
It bounces off at the same angle, and that's crucial for creating the virtual image.
So this principal ray, it's like the key to the whole thing.
It's one of the keys, yeah.
Mm-hmm.
There are a couple others that the simulation shows us too,
Yeah.
and together they give us a complete picture of how the image is formed.
Okay, I'm following along. So we've got these light rays bouncing off the mirror at specific angles, creating this virtual image. But how do we actually see the image? Like, where do our eyes fit into all of this?
That's a great question. So our eyes perceive the virtual image because some of those reflected light rays, they travel directly into our eyes.
Oh, okay. So it's the light rays that actually reach us, that create the image in our minds.
Right. And if we move our head, the position of our eyes changes.
Right.
And those rays change too. So the way we see the image also changes.
Huh. It's all about perspective then.
Exactly. And that's another thing that this simulation lets us play with. We can actually move the eye around in the simulation.
Oh, cool. So we can like see how the image changes from different viewpoints?
Yep. It's a really powerful tool for understanding how mirrors work.
Yeah, this is way cooler than I thought it would be.
And the simulation, it actually breaks down the whole process of forming the image into 3 steps.
Oh, okay, so it's like a step-by-step guide.
Yeah. First, it shows us a dotted line, which represents a virtual ray. And this helps us figure out where the virtual image will be.
Okay, step 1, the dotted line. Got it.
Then it shows the actual ray of light traveling from that virtual image point to the observer's eye.
Okay, so that's how the light actually gets to us.
Right. And finally, it shows the ray from the top of the candle reflecting off the mirror.
So it's like connecting the dots.
Exactly. The simulation shows us how the light goes from the candle, bounces off the mirror, and then reaches our eyes.
Step by step. Awesome.
And the best part is it's interactive. You can change the position of the candle and see how the virtual image moves accordingly.
That's cool. So it's not just a static picture. It's like a little experiment we can do.
Exactly. You can play around with it and really get a feel for how mirrors work.
I like it. So this is pretty amazing stuff, but I gotta ask, like, how realistic is this simulation? I mean, mirrors in real life, they aren't perfectly smooth, right?
You're absolutely right. The simulation, like most models, it simplifies things a bit. It assumes a perfectly smooth mirror which reflects light in a very precise way.
Okay, so it's like an idealized version.
Yeah. But in reality, surfaces are a little bit rougher, so light scatters a bit more.
Right, so it's not a perfect reflection.
But even with those imperfections,
Hmm.
the fundamental principles that we're seeing here, they still hold true.
Got it. So it's a great starting point to help us understand the basics.
Exactly. And once you understand the basics, you can start to think about how things might be different in the real world with all its complexities.
Okay, that makes sense. So we've got the simplified version down, but I'm guessing real-world mirrors have their own quirks.
Oh, yeah.
So yeah, that's a deep dive for another day.
Absolutely. There's always more to learn.
So much to explore. I'm already fascinated by just this basic stuff, though.
It is pretty mind-blowing when you think about it.
Yeah, like the idea that the image isn't really behind the glass. It's just our brains interpreting the light that way. It just makes you question what else we're seeing that might not be quite as it seems.
That is a fascinating point.
Yeah.
And it leads us to a pretty crucial question. If our perception of images can be so easily manipulated by something as simple as a mirror, what does that tell us about the nature of reality itself?
Whoa. Okay, now we're getting
A
philosophical.
little bit, yeah.
Yeah.
But it's a question worth pondering.
It is. It's a big one. We might need some time to think about that one.
Definitely. It's not a simple answer.
Well, I think our listeners are going to have a lot to chew on after this conversation.
I hope so.
And speaking of more to chew on, we've got more of this deep dive coming up.
That's right. We've only just scratched the surface.
Oh, to speak. Ha!
Exactly. We'll be back soon to explore even more mind-bending applications of mirrors and reflection.
Sounds good. All right, listeners, stay tuned for more mirror magic coming up after the break.
Okay, so we've covered like the basics of how mirrors make those ghost images, the virtual images, right? The fundamentals.
But I kind of want to get into some, like, real-world examples now, you
Mhm.
know? You mentioned before that these ideas are behind telescopes and cameras and stuff.
Yeah, all sorts of cool technology uses these principles.
So let's start with telescopes. How do they use mirrors?
Well, telescopes use mirrors to gather light, right, from really distant objects, like
Yeah.
stars and galaxies and things.
Okay, so they're like using mirrors to see things that are really far away.
Exactly. Imagine trying to see like a candle flame millions of miles away.
I don't think I could even see that across the room.
Right. You'd need a huge mirror to collect enough light to make it even visible.
So it's like a giant version of the mirror we were talking about in that simulation.
Kinda.
Hmm.
But telescopes often use a special kind of curved mirror called a concave mirror.
A concave mirror? Okay, so it's not flat.
Nope, it curves inward, and that shape helps it focus all the incoming light to a single point.
Oh, so it's like concentrating all the light.
Exactly. And that point is called the focal point.
Focal point, got it. So why is focusing the light so important?
Well, by focusing all those light rays into one tiny spot, the telescope makes the image way brighter.
Oh, I see. So it's like amplifying the light.
Exactly. Like
Yeah.
if you use a magnifying glass to focus sunlight into a beam,
Hmm.
it gets really intense, right?
It can even like start a fire.
Exactly. And in a telescope, this lets us see things that would normally be way too faint for our eyes to pick up.
So it's not just about collecting more light, it's about like concentrating it too.
Precisely.
Huh.
And that's all thanks to those same laws of reflection we were talking about.
The angle of incidence equals the angle of reflection.
Yeah. But now we're applying it to a curved surface. So the way the light rays behave is a little different.
Okay, so curved mirrors change the game a bit.
They do.
Hmm.
But the basic principles are the same.
Got it. So we've talked about telescopes. What about cameras?
Ah, yes, cameras.
They use lenses, right? Are those doing the same kind of thing as mirrors? Just in a different way?
You're on the right track. Lenses and mirrors both manipulate light, but they do it through different processes.
Okay, so what's the difference?
Well, mirrors reflect light, right? We've been talking about that.
Right. Bouncing off.
Exactly. But lenses, they refract light.
Refract. So what does that mean?
It means they bend the light as it passes through them.
Oh, so the lens in my phone camera, it's bending the light that's coming from the thing I'm taking a picture of.
Exactly. And by bending the light in just the right way, the lens can focus it to create a sharp image.
So how does bending the light actually create a picture?
Well, just like a concave mirror can focus light to a point clean, a camera lens takes all the light bouncing off a scene and bends it to create a focused image on a sensor.
A sensor. Okay.
Yeah, it's like a tiny little chip that captures the light.
So it's like projecting a tiny version of the world onto the sensor.
Exactly.
Yeah.
And actually projects an upside-down version.
Wait, what? Upside down.
The lens naturally forms an inverted image.
So my phone is taking upside down pictures all the time.
It is. But don't worry, the camera's software flips the image right side up before you ever see it.
Oh, thank goodness. That's so
Yeah.
weird to think about.
It is kind of strange when you stop and think about it.
So mirrors and lenses both manipulate light to create images, just through different ways.
Exactly. But they both rely on those same laws of physics we talked about.
Right. Whether it's reflecting or refracting, it's all about how the light behaves.
The angles, the materials, it all matters.
Okay, I'm getting it. Okay, one more gadget. I gotta ask about lasers.
Lasers.
Ah,
Yes, those are fun.
they're all about focused light, so I'm guessing mirrors play a role there too.
Absolutely. Lasers actually use mirrors to amplify and direct the light.
Amplify, so they make the light stronger.
Exactly. Imagine a beam of light bouncing back and forth between two perfectly aligned mirrors.
Okay, I'm picturing it.
That's basically what's happening inside a laser.
So it's like a light bouncing chamber.
Pretty much.
Hmm?
And with each bounce, the light stimulates the atoms in the laser material.
Okay, things are getting a little complicated now.
Basically, it causes the atoms to release more light particles, more photons.
So it's like a chain reaction.
Exactly.
Okay.
And that builds up a really intense, focused beam of light.
Okay, I think I'm following. So all that bouncing around makes the light stronger?
And more focused.
Yeah.
And then one of those mirrors is partially reflective.
Right. So some of the light can escape.
Exactly.
Yep.
And that's the laser beam we see. It's super powerful and focused because of all that bouncing around between the mirrors.
Wow. It's like the mirrors are training the light to become a laser beam.
That's a great way to think about it.
Okay, so we've covered telescopes, cameras, lasers. Is there anything that uses mirrors that doesn't sound like sci-fi?
Good question.
Mhm.
Well, even something as simple as a rear view mirror in a car uses the same principles.
Oh, yeah, good point.
It's a convex mirror, which means it curves outwards.
Right, and that makes things look smaller.
Exactly. That curve gives you a wider field of view,
Yeah.
so you can see more of the cars behind you.
So it's like a funhouse mirror, but helpful for driving.
Exactly.
Yeah.
And speaking of funhouse mirrors, they also use the principles of reflection to distort images.
Right. That's where all the fun comes from.
It all goes back to how light interacts with different shapes and surfaces.
Okay. My mind is officially blown. From telescopes to cameras to lasers to rear view mirrors, it's all connected.
It is. It's all about light and reflection.
And it's everywhere. It's like this whole hidden world that we don't even realize is there.
But it's a crucial world. It's the world that lets us see and understand the universe around us.
It makes you wonder, though, like if all we're seeing is reflections, how much of what we perceive is actually real?
Now that is a deep question, and one that philosophers have been debating for centuries.
Okay, maybe we're getting a little too deep for this deep dive.
Maybe so, but it's definitely something to think about.
It is. And I think our listeners are going to have a lot to ponder after this conversation.
I hope so.
But before we get too lost in existential questions, we've got one more part of this deep dive coming up.
That's right. We'll be exploring even more applications of mirrors and reflection, and maybe even tackling some of those philosophical questions head on.
Sounds good. All right, listeners, stick around. We'll be right back after a quick break.
Okay, so we've gone from like telescopes looking out into space to like simple rear view mirrors in our cars.
Quite a range.
Yeah. It's amazing how many things use mirrors and lenses and stuff.
It really is. And,
Yeah.
and before the break, you mentioned something about fiber optic cables.
Oh yeah, those things. How do those fit into all this talk about mirrors and reflections?
Well, fiber optic cables, they're those thin strands of glass or plastic that transmit data as light pulses over long distances.
Right, so like the internet and stuff.
Exactly. And the thing that makes them work is a phenomenon called total internal reflection.
Total internal reflection. That sounds kind of
it's pretty quick. Basically, remember we talked about how the angle at which light hits a mirror determines the angle it bounces off?
Yeah, the angle of incidence and all that.
Right. Well, in total internal reflection, the light hits the boundary between two materials at such a steep angle that it gets completely reflected back into the first material. Okay, so instead of passing through to the other side, it just bounces back.
Exactly. It gets trapped inside. And in a fiber optic cable, that means the light can travel for miles and miles, bouncing back and forth inside the cable.
Really? Miles?
Yeah, and because fiber optic cables are made of these super pure materials, the light signal barely weakens, even over those long distances.
Wow. So all the data, all the internet traffic, It's all riding on beams of light bouncing around inside these tiny cables.
It is. It's pretty wild when you think about it.
It is wild. So all thanks to total internal reflection.
Exactly. And it all goes back to those same principles of reflection we've been discussing. The angles, the materials, it all plays a role.
It's amazing how these simple ideas can lead to such complex technology.
It really is. And who knows what other amazing applications we'll discover in the future.
Well, you've definitely opened my eyes to the wonders of mirrors and reflection. I used to think they were just, checking my appearance. But now I see them as these gateways to understanding the universe.
That's a great way to put it. And that's the beauty of curiosity, right? By taking a deeper look at the everyday things we take for granted, we can uncover a whole world of knowledge and wonder.
I couldn't agree more. This deep dive has been a total mind trip. And I want to thank you for being such a fantastic guide.
It's been my pleasure. And to
Okay.
everyone listening out there, remember to never stop questioning, never stop exploring, and never stop being amazed by the world around you. Who knows what incredible discoveries await just beyond the next reflection?
That's a wrap for this deep dive into the world of mirrors. We'll be back soon with another fascinating topic. Ready to take you on another journey of knowledge and exploration? Until then, stay curious.